Hi everyone, this is the next video in the series. We're going to be looking at the derivatives of functions with bases other than e. The chapter also has applications in it. We're going to do those in class, but these are the objectives for this video. Okay, so let's start off with a definition. The definition of a logarithmic function to the base e of a function that doesn't have base e as a base, log to the base a could be any value, any number, x equals, all right? And we're going to learn this, use the concept of change of base. Now, remember that I told you that we often don't use change of base formula anymore because we have this function on our calculator. But this is an idea that is worth reviewing because remember that on your calculator you have log and you have natural log. Remember that log is base 10, the common log, and natural log is base e. Well, in calculus we are exclusively using natural log. But we learned that we could actually write log base 10 of 5 and then divide that by the log base 10 of 2. We also know that we could do that with the natural log. We could say that the natural log of 5 over the natural log of 2, and these will both be the same value. This is the same value. So using change of base on the definition of a logarithmic function would be the natural log of x over the natural log of a. And we're going to use that to derive some derivative, or take the derivative of different formulas, because we know how to take the derivative of the natural log of x, and the natural log of a is a constant. So we know what to do with it as well. Okay, so change of base is one idea we need to keep in mind. The other thing we need to keep in mind is something you may or may not have learned in pre-calculus, and that's that you can write a base to the x power. You can write this as something that looks like this, all right? So how did they get to that? Well, let's look. We've got a to the x, right? And then if we take the natural log, let me write it this way, the natural log of any value, let's say x, and we take e to that power, we're just going to have x. So in other words, I could just write x as e to the natural log of x, knowing that e to the natural log is going to be 1. All right, so let's do the same thing here. Let's say e to the natural log of a to the x, right? Knowing that this is 1. And then remember that our power rule says we can put the exponent in front. So we would have e to the x natural log of a. So say for instance we had 2 to the x power, and we want to write that as that using this technique. So I would say that that was equal to e to x the natural log of 2, knowing that the natural log of 2 is a constant. Okay, so that's what this is about. All right, so now if we start doing derivatives, we're going to also use this concept. I'm going to make myself a little room here. Okay, so here where I have the derivative of a to the x, right? So I'm going to just write over here, if I write that as e to x natural log of a, and I take the derivative of that, right, then I am going to have this e to the x natural log of a times the derivative of this, which is just natural log of a. Well, if I substitute this back in, I have a to the x natural log of a, and that is the formula for finding the derivative of a to the x, where a is any constant. Okay? So then This next one then is the same thing, it's just u. So when you do this, remember that a to the u would just be this. A to the u would be the same thing as e to u natural log of a. So if we take the derivative of this, we end up with e u natural log of a times the derivative, which is the natural log of a, times the derivative of u. So chain rule again. That's chain rule. So number 2 adds chain rule to it. So that gives me a to the u times the natural log of a. That looks about the same. But then we take the derivative of u. Chain rule again. Okay, hang on. Okay, so I ran out of room on the last one. So let's talk about then how we would find the derivative of numbers 3 and 4 on this list, finding the log. Okay, so we're going to use change of base. We use that other for that. We're going to use change of base on 3 and 4. Change of base was, remember, if we have log to the base a of x, we would write the natural log of x over the natural log of a, and then take the derivative of that. All right, so if I take the derivative with respect to x of the natural log of x over the natural log of a, remember natural log of a is just a constant, so I would have 1 over the natural log of a times the derivative of natural log, which is 1 over x. So that's going to give me then, if I just rewrite it, 1 over the natural log of a times x. Probably a better way to write that was with the x first. Just like that. All right? So then you can imagine that number 4 is the chain rule. So if I take the derivative of the natural log of u over the natural log of a, then it's going to look very, very similar. I'm going to have 1 over the natural log of a times 1 over u times the derivative of u. Chain rule. Okay? So I'm going to have the same thing over here. I'm going to have 1 over the natural log of a times 1 over u times du dx. Okay, so here's some pretty simple examples. This is like number 1, right? The base is 2. So the derivative of this function would be 2 to the x times the natural log of 2. Done. Number 2 is like number 2 on there. It's using more of the chain rule. So y equals 2 to the 3x times the natural log of 2 times the derivative of 3x, which is 3. That's it. All right, then at the bottom, this one is going to be a lot like number 3. So I have, if you did change of base, right? Change of base would be the natural log of cosine over the natural log of 10. So the derivative of this function then would be 1 over the natural log of 10, that's my constant, times 1 over cosine x times the derivative of cosine x, well this is like number 4, is negative sine x. Right? So you could just write it 1 over natural log of 10 negative times tangent x. Sine over cosine, tangent x. So once again, the hardest thing is like which rule do I use? Well, this looks a lot like number 2. This looks like a to the u. So if I rewrite this, right, then I know I've got y prime is going to be 5 to the square root of x, I'm just going to write it just like that, times the natural log of the base, times the derivative of x to the 1/2 power, which is 1/2 x to the negative 1/2. So if I rewrite all this stuff, I'm going to have the 5 square root of x times natural log of 5 on the top, the 2 and the square root of x on the bottom. Kind of ugly, but not too bad. So here's another example. I've log to the base 12 of e to the third of x to the 3rd power. So I'm going to rewrite that in terms of natural log. So I've got natural log of x to the 3rd power, so the exponent goes out front, and then the natural log of 12, and then I'm going to take the derivative. So I have 3 over the natural log of 12, that's my constant, times 1 over x. And here's another example, which I wrote really quickly. F of x equals e to the 3x minus 3e to the x. And so then if I go to take the derivative of this, I'm going to have 3e to the 3x. That was the old way of doing it, right, because e was the base. And then minus, what I have here is, I just rewrite it, 3e to the x times the natural log of 3 times the derivative of e to the x, which is just e. And here's our old favorite, the product rule. So when I go to take the derivative of this, I do first times the derivative of the second, which is 5 to the x times the natural log of 5 times the derivative of x, which is just 1, plus 5 to the x times the derivative of the first, which is 5x to the fourth. Now, I could factor out if I wanted to simplify, and I want to show you how you can do that, right? I could take out an x to the fourth from both terms. I could also take out a 5 to the x. So if I do that, then I'm going to have x left here and times the natural log of 5 plus, and then just a 5. And so that would be it simplified. Okay, so the last thing I want to do is go over some of these and how they look different, and we're going to end up with this one. But remember that e to the e power is just a number, and a derivative of a constant is just 0. So e to the e is just a constant. The derivative of e to the x is just e to the x. The derivative of x to the e power is just the power rule. So e is just a constant. So I would say ex to the e minus 1. And then you get to y equals x to the x power. All right, so let's look at this one down here. So if y equals x to the x power, and we write it according to our e natural log of x, x in front, right? And then we take the derivative of this, right? We take the derivative of it, then we have e to the x natural log of x times the derivative of the top, which is the product rule. So first times the derivative of the second plus the second times the derivative of the first. Okay, then we replace this because we know what this is. This is really just x to the x power. We know that this is just 1. So we actually end up, y prime of this is x to the x power natural log of x plus 1. And that's it. So there's a lot here, a lot of e's, a lot of x's, a lot of all kinds of things. But if you'll keep in mind what's a constant, what's not, the change of base, and then this technique of writing it e to the natural log power, I think you'll be okay. So we're going to practice this in class. See you then. All right, one last thing. We've talked a whole lot about taking the derivative, but we haven't talked anything about taking the integral of a base other than e. So I have an example here, the integral of 2 to the x dx, that's an a to the x, right? You have two options. You can convert it to base e, or you can integrate directly using the formula. So honestly, number 2 is the best method, but I'm going to show you how you can do that a different way. And so what we're going to use is this idea that a to the x is equal to e to the x natural log of a. And so that's what we're going to do here is we're going to convert this to that. So I'm going to have e to the x natural log of 2 dx. Well, that gives me u substitution. The u is the exponent, as it often is. Natural log of 2 is a constant. So du, the derivative of that is just going to be the natural log of 2 dx. Okay, well, we notice that it doesn't have that there. So if I add the natural log of 2 to this, then I have to do the 1 over the natural log of 2 as my constant. And then once you take the integral of e to the x, it's just e to the x. So it's 1 over the natural log of 2 e to the x natural log of 2 plus c. Now, one additional step is to resubstitute that back, right, for this. So your actual answer will be 1 over the natural log of 2, 2 to the x plus c. All right, so that's an awful lot of work to get to this. So what we're going to do instead is the formula, which is basically the integral of a to the x dx is 1 over the natural log of a, as you can see by the pattern there, times a to the x plus c. And then the only difference to that is making sure that your u is satisfied. You know, if that's u, then you've got to make sure you have a du. But this is the formula. So once again, if I have the integral of 2 to the x dx, it's going to be 1 over the natural log of 2 times 2 to the x plus c. So once again, this is going to be one of those times when memorizing the formula is probably a good idea. So anyway, that's it for this, and I will see you in class.